Sorry, just getting really wrapped up here, really emotional, all right? Today's Violent Earth topic is all about the great movie Armageddon. Okay, no. All right. Okay, it's just part of it, all right? We're going to use that as a little bit of tribute to talk about asteroid impacts, all right? Okay, the Armageddon thing, go watch it on your own, go have fun, right? Great movie, great song, as you can tell, I love it. Makes me a little sappy inside. But let's talk about the violent part of that movie, which the Earth was going to get smacked by a gigantic Texas-sized asteroid. And then Bruce Willis saved the day. Kind of. Okay? I think it was actually the other guy, kind of. Yeah, anyway. A lot of people saved the day there, especially Liv Tyler. Today in Violent Earth, we are going to talk about arguably the second most violent event that we've talked about in this course. Now, the first one, I would say, the giant impact hypothesis, where boom! Thea ran into the Earth, and we have, voila, Moon on the other side after all the ejecta slowed down, right? That was an impact hypothesis. Now, what we're addressing today are all of these smaller impacts that have happened through time, asteroids, relatively large rocks that have come from outer space and have hit our planet and caused dramatic changes on the surface of the Earth. Okay, now, today we're going to look at a couple of different impacts. One of these really recent impacts, very beautifully preserved crater in Arizona, the Barringer crater. We'll look at a couple of older impacts. These ones, they're in one case billions of years old, so we're not going to look at that in context of life. But the last one we will. The last one is a very famous impact, the crater called Chicxulub that's left over off of the Yucatan Peninsula. And that one's very famous in the context of life, or how life on Earth was affected by this. Okay, so here's our spiral of time, some of the stuff that we've been through. I moved a couple of these images, but here's, the cosmos, accretion, planetary accretion, making protoplanets, ignition of the sun, expelling photons, and let there be light. Boom, creating the moon, layered, differentiated Earth into its multiple layers, compositional and mechanical. We have the making of crust of the Earth. It took a very long time to get to modern day plate tectonics in the Proterozoic. Volcanic eruptions as the sort of daily, everyday action of making crust, as well as emplacement of granite. The supercontinent cycle, or the Wilson cycle, of the accordion moving back and forth through time of all the continents over billions of years we've had before. And then Pleistocene and snowball Earth glaciation. So there is kind of a recap of the class, but let's move forward to today's violent event. So the Barringer crater, here's a panoramic view from the visitor center. The Barringer crater here is a crater that's only about 50,000 years old. This impacted the Earth during Pleistocene time, during the ice ages. So Arizona wasn't barren, right? It wasn't lifeless like it is today. Remember, the ice sheets had come all the way down about to the latitude that I'm at, right? Only a couple hundred kilometers to the north of me. So the climate of overall North America was much different. And during that climate period of North American ice being this far down, the gap of water coming off of the Pacific Ocean and the gap between the tropics and the ice sheets was a very windy, rainy gap, as water coming off of the Pacific was very laden with moisture, and it would dump on North America and collect in these nice little closed basins, otherwise known as lakes, right? Closed basins that fill with water, you call it a lake. And Arizona was no exception to that. This picture from an airplane, not my picture, this airplane picture, you can actually see that this large area out here, this large plateau, it's all relatively the same even, same even topography. This was a lake 50,000 years ago, a relatively shallow lake, and the crater out here in the middle of this. So it is speculated that the Barringer meteor, the iron nickel meteorite, about 50 meters in size, it's a sizable rock, moving at about 8 miles per second, produced a 10 megaton explosion when it smacked into this shallow lake and into the surrounding landscape that's here. Okay, now the lake sediments, if you look at these, the rim around here, these are actually lake sediments. This is partially how the history of this lake is known. And what's preserved in the ring around this was part of being able to confirm that this was an impact crater, is there's small structures called impact structures or cone structures. As a rock or a stable monolithic piece of something is struck from the top, oftentimes they shatter in a cone type of shape. Think of glass. Anytime you've seen, like, say that your windshield, when there's a crack that starts, it kind of makes this arcuate shape. It doesn't just go right across. But the way that crystalline structures like that, not that glass is a crystalline structure, it's an amorphous solid, but they oftentimes have some sort of curvature of the breakage patterns in those molecules. And that happens to rocks as they get, bam, smacked by something. They oftentimes form these impact, or these conical type of structures, or impact structures that are around here. So that was one thing that helped identify this as an actual crater. Why would we have to identify it as a crater? Look at it, right? It looks like a meteor crater. Or does it? Okay, in the next slide, as I advance this forward, this is a YouTube video. I'm not going to show it here in the video. I'm not going to do a video of the video. And I'll make the URL link available below. But that short video that's available in the Visitor Center here at Barringer Crater does go through a little bit of how this was identified. And at that time, this is early 1980s, late 1970s in geology, many geologists were very opposed to catastrophic ideas, right? To big earth catastrophes that have shaped the whole land, fire and brimstone and floods and all this kind of stuff. And this is kind of coming out of the previous 100, 150, 200 years, where geology, early geology, was very formed on the back of what might be considered biblical geologists or flood geologists, right? People who are looking for evidence of Noah's flood and then deciphering the rocks in context of these biblical mythologies. So when it was determined that there's no global flood that could have occurred by looking at different sedimentary rocks around the world, a lot of geologists became anti-catastrophists. So they didn't want to see that catastrophes were responsible for changing the face of the earth. Instead, there became this idea called gradualism, that the changes that we see on Earth, the physical features that we see here on Earth, are the cumulative product of slow changes through time. Like rivers, they just flow and then slowly they meander through time to deposit stuff or to erode the thing away. Mountains slowly rise. So there was kind of a backlash to these ideas that we're talking about in this class, all about violence, right? Catastrophic violence to the earth. So Barringer Crater, it was argued, was a volcanic crater. That this lake, the volcanic products, the magma dikes that were coming up from below, they encountered groundwater to make a phreatomagmatic eruption, which is just like a steam eruption, where the lava was heating up the water to make the steam expand, and this was like a steam explosion, and that made this giant pocket out here. Now these things do exist. They're called Mars. There's several of them out here in eastern Oregon. Big Hole is one of them. Big Hole, that's kind of a great name for one. Or Hole in the Ground, that's another one out here in eastern Oregon. And those two are confirmed to be these like steam explosion type of things. So Mars do exist. They are M-A-A-R-S. They are known to exist in geology. And just this isn't one. This is an impact crater, no doubt about it. Okay. So this is the collected material that is thought to be the protagonist here to make this crater. Now, I just like to use Barringer crater first to show that, hey, look, there's a symmetry to this. This is kind of what a meteor crater looks like. This is a small one. Now let's go on to violent ones. Okay, let's go on to bigger ones. Okay, here's that short video. Again, the URL link will be available below if you want to take a look at this. Now, I want to point out that geometry of impact craters, that there's a threshold here to the geometry or the size of the impactor, which then also determines the speed and the size of the blast, that changes the geology of the underlying impact, or what's left over after the impact. So, if you're a relatively small object, and you're penetrating not very deeply with not a lot of force, then that might create something like a simple crater, where there's, shatter cones that are down here, impact cones that are down here, some debris like breccia debris that's in here, maybe some ejected material on the edge, but generally a concave type of shape, right? That is quite different from what's called a complex crater, where this is a big thing that hits with a lot of force, and this penetrates deeper into the Earth's crust. I'm not talking like a kilometer or anything. I'm just talking several hundred meters of pressure, high pressure, into the Earth's crust. What changes is the rheology, or the actual properties of the rock below that. They become almost like, they behave almost like a Newtonian fluid during that impact. So as the impact pushes them down, that Newtonian fluid drips back up, kind of like a drip into water, right? You drip something into water, sometimes there's that little anti-drip, or that little backwards drip that comes back up. This is just like that, where the rheology of the rock has changed enough to flex down and then to flex back up, and to make a central peak in the middle of the crater. So these craters, you can see these craters on the moon. You can see these really anywhere that there is evidence of cratering. You can see both types of craters, small things with lower amounts of pressure, and bigger things with larger amounts of pressure. So the threshold is about impacts larger than 4 kilometers on Earth with an Earth-like atmosphere produce craters with a central peak. Hydrodynamic flow of material lifted by inward collapsing crater walls, while some impact shattered debris is briefly turned to fluid by strong vibrations. Okay, I think that's super cool, right? This has to be something pretty amazing and impactful to make rocks like fluid, but they're not molten. They're just like fluid, but they're not melted, just like fluid, right? Okay. So this is a global map showing a whole distribution of known and mapped impact craters. None of these on here are argued or are subject to which angle you're looking at, or blah, 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 or geologists haven't looked. These are all very well accepted meteorite impacts that are preserved on the surface of the Earth. Now let's back up a second to last week's conversation, and notice I'm wearing the same exact clothes this week, because your last week was like 15 minutes ago for me. Anyway, the tectonics of the Earth are continually consuming oceanic crust, and it's covered by an ocean, so we might not really get to see impact craters that are preserved in the ocean, if there are any. Presumably there are. Then the surface, or the land surface of the Earth, the cratons and the continents, remember, those are continually undergoing deformation. Orogenies, earthquakes, volcanism, right? They're continually being messed up. So the fact that we can identify so many of these is pretty darn cool. But they're not all simple, right? Well, simple craters and complex craters, they're both. But they're not all geologically simple to identify, right? Is we have to go through different means, besides just a big bowl sitting there on the Earth like Barringer crater, to determine that these things are craters. Okay, and I want to show you a couple really cool examples from the geologic literature I think are pretty cool before we get to the big impact crater. So what I like also is you can see how densely populated craters are identified in North America, in parts of Europe, not so much, right? So there is a preservation, not just a preservation bias here, but also a bias of where do people actually go hiking, looking at rocks, right? So there are areas that are relatively or poorly traveled quite as much by geologists looking for these things or looking for evidence. Okay, oh, I also want to point out one that's missing from here, relatively recently identified, I think in 2016, fairly recently identified impact in Greenland, that as the ice has melted away and exposed some of these rocks, we can now see an impactor that formed sometime before the Pleistocene, or at least during an interglacial time period, up here or multiple impacts, I believe, up here on the western Greenland ice sheet. I think I'll also put the link to that in the video links below. All right, now one of these that I think is a really cool discovery story, this is the Chesapeake Bay impact crater. Now, if you look at the map today, it's really difficult to determine that there's anything there, right? You kind of have this curvature of the eastern United States, but, you know, is that really related to the crater? Maybe yes, maybe no. I mean, partially some of this inherited stuff, so yes. But there's really no observational evidence from the surface that would suggest that there is a crater that's here. Now, the identification of this then didn't come from mapping from the surface down. Instead, this came from looking at the rocks below through petroleum exploration. Yeah, way out here in the Chesapeake Bay, there are petroleum-bearing shales that can be drilled down, and petroleum-bearing reservoir rocks that can be drilled down to extract some of that petroleum. Now, in some of these cores or some of these areas, you know, we're always curious about what's a little bit deeper, right? Where is some of this the oil-bearing material coming from? If it's up here in the reservoir rock, how deep did it come from? So I think out of somewhat of curiosity, there were some of these holes that went a little bit deeper, and they found breccias. They found a really interesting different rock type that probably shouldn't have been there given the overlying geologic context. So that encouraged yet more curiosity and more research that developed different areas to drill deeper into, not necessarily for petroleum in this case, but instead to search out this geologic formation. And what was revealed, here's a generalized cross-section of all of this. Here's the crystalline basement. This would be some of those rocks that the Acadian orogeny, the Allegheny orogeny, those things that we talked about building the Appalachians. That's all this stuff that's here. And then on top of that, as Africa has rifted away, you have all the sediments that were draped on top of this. Well, during all of that sediment draping, bam! It was hit by a meteor impact or an asteroid impact that made one of these huge craters with a central peak, as some of that rock was kind of converted to a Newtonian fluid, at least for a portion of time, to make a nice central peak. And then all the infill, or the area filled in with breccias from its own destructive processes. And then on top of that, more sedimentary rocks were deposited that covered this up. This is 35 million years ago. So it's had 35 million years of North America's rivers dumping out into the ocean to make a continental shelf. And it's all covered up. So if it was not for petroleum exploration and kind of curiosity to go a little bit deeper, an impact like this would have never been identified. Okay? So why would that be important? Why would it be important that we know every little impact that's out there? And every little impact age. Towards the end of this lecture, we'll talk about something called the Torino scale, which is kind of an idea of how much danger we're in, like in this Armageddon type scenario. We have astronomers identify near-Earth asteroids all the time, and they monitor these things, and there's a scale to how dangerous some of these things are. What also helps to know, there's a threshold to the things we can actually see and identify, the size of the rock. So it also helps to know, looking geologically at the evidence, of how often these things occur. If we would have not identified this one, then maybe, our calculations of the recurrence interval of a rock hitting the Earth of this size would be off. Okay, I hope that makes sense. So the more data that we have, or the more of those data that are accumulated, the better idea we have of the recurrence intervals of some of these impacts. Okay, let's look at a slightly older one. This is about 2 billion years old. This is one of my personal favorites. I think it's the story is also pretty cool, but I like this one because it's been tectonically deformed. So here's the Sudbury Impact Crater. You can see it's really kind of an oval shape now, and here's the geology of that. It's kind of an oval shape now. That oval shape is only an oval shape because this circle was squished like this by the Grenville orogeny, right? Now, in last week's lecture, you might remember me mentioning the Grenville orogeny as something that stitched back up the continent after it was rifting apart, the mid-continental rift, when about 1 billion years ago, North America started to rift apart, and then the Grenville orogeny stitched it all back together, okay? So it never had a full rift. Now, the Sudbury Impact Crater, again, 1.8 billion years ago, it's 10 miles wide, and this flung material all over Minnesota and Wisconsin. One of my favorite examples of that, over here in the Gogebic Range, or the Iron Ranges of not northern Minnesota, but of northern Wisconsin. These iron ranges, there's banded iron formations that are preserved there. And in those banded iron formations, you can see little broken up remnants in some of these outcrops, in some of these places, that are speculated to be ejecta from this event. They were ejected outwards and then deposited in these areas that banded iron formations were accumulating. Now, banded iron formations are a very cool rock. We're going to talk about it in a couple of weeks when we focus on poisonous gases here on Earth. Now, the Sudbury Impact Crater, again, this is a fairly large crater. It's 10 miles wide, and again, this is a really old one. So this shows that even when these things are deformed and they're not perfectly circular, we can still identify them, again, not by map evidence, but by geologic evidence of looking at the shattered, brecciated areas, by distally flung materials, and a mineral that forms, or an impact quartz mineral that forms during this process. Okay, this is again an older crater here, younger than the Sudbury crater, and this one is of local interest to us. As far as I know, there is not a ton of data about this crater. This is a crater. This is geophysical imaging of the lower lithosphere, or sorry, mid-lithosphere. That's meant to show approximately where this crater might be. And the main evidence for this crater comes from those minerals, the shocked quartz, that form during the impact. They get shocked, and the quartz grains, the quartz minerals, they actually change into a slightly different mineral called coesite. It's still quartz, but it's a slightly more dense form of quartz, shocked quartz. And that quartz has been found in rivers all around in this area. So here's the boundary of Oregon and Idaho. Here I am in Ontario. This is the state of Idaho, the Snake River Plain, the Beaverhead Mountains, southwestern Montana, Sawtooths, Seven Devils. And underneath all of those mountainous areas is suggested that 1.2 billion years ago, before these mountains were ever even here, they're young granite mountains, there was an impact crater there. And how do we know, or how has this been proposed? It's been proposed by this area weathering away, and the minerals that are weathered away into the local rivers. If we pick up sand from the rivers and we look through the sand, there are these little minerals, these little bits of shocked quartz there in the sand. So these pieces are amazing that we can reconstruct some of this stuff, right? From little pieces of sand, little grains. Now, this is proposed. Again, there's not a ton of evidence that's come from this. The grains were one of those. And then there was additional evidence that came from geophysical imaging to look to see if there's any deformation in there. And sure enough, there does seem to be a deformed area beneath those mountains. So the impact may have in thin crust and triggered a delamination event to allow the mountains to uplift. So there are old rocks here, and as that impactor impacted the area, the lower lithosphere may have decoupled or delaminated away from the upper lithosphere and caused a rebounding event. So there was uplift in this area, and that rebound being shown here. Again, this is an interesting one, but not one that is, kind of nail in the coffin like the Sudbury impact or the Barringer crater that's out there on the surface. Okay. Now, a relatively recent one to come on the other side of that. This is one that left no impact crater. So yeah, there are rocks that fall from space that don't leave impact craters. We might call them shooting stars, right? Every time you see a shooting star, that's a piece of space dust or a piece of space rock, a small little bit that's coming to the atmosphere, and as that material is volatilizing in the atmosphere, is being is lit up from all the bonds that are breaking, all the light there is that little ball, not ball, but that thing, that dust, that silicate material that's volatilizing in the atmosphere. So these occur not all that infrequently, right? Maybe not big ones like this, but I remember a few years ago there was one in Wisconsin. 2012-ish, there was one over Russia that was caught with a whole bunch of dash cams. Really cool sequences there of the going across the sky, and many dash cams had it. It blew out some windows. And even just a couple weeks back, there was one that was caught over New York, or New York State. So these shooting stars, right, or fireball events that go over cities, they do happen fairly frequently, I would say. Every couple of years, there's major big reports of them. And ones like this, however, about a meteor that broke up in the atmosphere, didn't leave a crater, but there's a large strewn field of all the broke up material as it came into the atmosphere. So there is material that was actually collected from this, but it wasn't big enough to leave an impact crater. Instead, there was an impact pressure wave. The atmosphere mowed down trees and forests for hundreds of miles, and this could be heard up to 1,000 miles away as it broke the sound barrier in the atmosphere. Boom! Right? The Tunguska event. All right, if you're interested in the sizes of different impact craters and kind of playing around with these things, I would suggest this Earth Impact Effects program. This gives you, I think you actually have 3 different planets to choose from: Mars, Earth, and the Moon, from what I recall. Maybe that's on the next one. But basically, you can put in the projectile's diameter, the projectile's density, whether this is an iron meteorite or a chondrite meteorite. You can put in the angle of the impactor, 45 degrees, 90 degrees, whatever you want to, 10 degrees. The velocity of that impactor, what it's hitting, sedimentary rock, igneous rock, crystalline basement, and then the distance from the impact. So what you can do at this last part is you can put in, if you're an observer of this impact, you can put your observable distance away to see how your area changes. Now, the point here then is to kind of see, okay, if a 10-meter rock moving at, coming in at 45 degrees, moving at 10 miles per second, impacted an area 100 miles from me, would I be safe? And so this is something that allows you to go through all of that and see that you'll really scare yourself if you get too into this, right? But remember that these rocks that actually hit the Earth are not all that common, okay? But this is a really good program that's been developed to show the impacts in different areas. Okay, so here's the impact crater. This is another one that's linked there, but here you can choose from the Earth, Moon, and Mars. Clearly there's differences for the main difference being the atmosphere, right? By the time the rock is falling to the planet, the mass of the planet doesn't matter all that much to the mass of the object. I mean, it's coming in, whether it likes it or not. It's the atmosphere of the respective planet or satellite that is going to really slow down or dampen that. So Mars having a much thinner carbon dioxide atmosphere. It's thinner, so it's less time for that to go through, but it's a thicker atmosphere as far as its composition of molecules. The moon has almost virtually no atmosphere, right? Hydrogen and helium particles, basically nothing out there. So anything that comes in just comes right in from space. The Earth, however, has a nice blanket of a whole lot of different gases, mostly nitrogen, carbon dioxide, ozone, water vapor, argon, that are all slowing down frictionally all of the materials that are coming in. And many of these things disintegrate in the atmosphere before they ever hit the Earth. Okay, so the atmosphere, again, kind of saving us from wreckage over time. Oh, look at that. Today's dose of violence, of course, brought to you by Armageddon. Actually, this is a little premature. We got a couple of things yet to go through, but I think, okay, what time is it? Been going for 32 minutes. We'll just finish it up, okay? Finish it up right now. Take a break if you need to. Pause the video, go tinkle, do what you gotta do. All right, what I want to do now is go through, after looking at these other impacts, we're going to talk about the big impact, the one that you probably know the most about, if anything, that asteroids can hit the Earth and destroy shit, right? Like destroy entire species. Not just one, right? But hundreds of species of Earth, causing mass extinctions of animals that will never come around again. And of course what I'm talking about is the dinosaur-killing asteroid, the Chicxulub impact crater that happened 65 million years ago. So here's a whole smattering of stuff that's over here. Here's a really good textbook diagram that shows these pterodons out here like happily flying, and there's a big rock that's coming over here to smack the Earth. Oh no, right? Or it's a funny image, and then sort of geography that's showing this a little bit better. Here's the Yucatan Peninsula down here in Mexico, and the impact crater is slightly on and off of the Yucatan Peninsula. Zoom in a little bit. Here's slightly on and then slightly off. And then here's some geophysical imaging of that, some seismic imaging to show the outline of that crater. Here's the coastline. So we know very well the existence of the crater, but that existence of the crater wasn't known forever. Okay, so we're going to kind of go back a little bit through the history of this dinosaur-killing asteroid. So clearly dinosaurs as fossils have been known for a couple hundred years, since Marsh and Cope went through their whole dinosaur collecting extravaganza back in the late 1800s to gobble up as many dinosaur fossils as they could. I mean, they weren't eating them, excuse me. I mean, to find as many dinosaur fossils as they could and name as many species as they could, the paleontology wars. Point there being that dinosaurs as a whole clade of organisms have been known for a long time, and even their fossils have probably been found for much longer than that. So point is, we've known that the dinosaurs went extinct at that level of geologic time, right? Or in the Mesozoic time period. There's no dinosaurs in the Cenozoic time period, or modern time period. And that extinction wasn't just to the dinosaurs. A whole bunch of different animals and plants, paleobotany, whole bunch of animals and plants, a lot of material. Oops. Equipment died the other day, so I'm coming back a couple days later to pick up the conversation after the tribute to Armageddon, all right, where I'm coming now to start a new bit of material coming off of those other random, it seems, asteroid impacts, or at least the impact craters that we were talking about, to come back to, I would say, almost a more famous asteroid, right? Or at least the
the dinosaur-killing asteroid, the main attraction when we're talking about asteroid impacts and violence here on Earth, or violent Earth. Now, this impact, we have a whole lot of data about. Why? Partially, this is called, by the way, the Chicxulub impact crater. Why? Because these guys, the dinosaurs, who we all know and love, right? Every kid has had their time with dinosaurs. They went extinct during or just after this impact. This impact was very likely the, if not the main cause of their demise. This certainly was involved in the very end, or cutting short their demise. And we'll talk a little bit about those things in a bit. So the Chicxulub impact crater, we'll go over some basics, talk a little bit about dinosaurs and their poor demise. But don't be so sad about them. Geez, you guys. There's some silver lining here. And then what I always like to do is go through some of the details. How do we know this stuff? Right? What are the things that we can see on the surface or in the rock record of an event like this, of this violence? So first of all, here's another artist rendition. That last picture, of course, is an artist rendition of an asteroid or of this size impacting the Earth. There's some pterosaurs flying away in the distance, and here's the giant rock that is hitting the Earth, maybe sending a gigantic tidal wave or vaporizing the ocean that's over here. I'm not really sure what the artist meant in this, but you do get this sense of doom, 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 right? Of this gigantic rock creating, something going on over havoc. Then in the small inset over here, you can see the trajectory of the asteroid into the atmosphere. It's putting it over here at the Yucatan Peninsula, Mexico. Same thing up here, this inset. You can slightly see that quite a bit better. I want to go back to this one, though, and point out that the plate tectonic configuration is a little bit different than it is today, right? Africa and South America a little bit closer together, a little bit of a different configuration up here in Western Europe. Mexico, the whole isthmus looks quite a bit different. This is 66 million years ago, right? So things should look different. Then if we go now back up to a modern day picture or modern day view of where this impact crater occurred, here's the Yucatan Peninsula of the nation of Mexico. The Yucatan Peninsula out here, relatively flat today. It is mostly oceanic, a lot of carbonate rocks. And as far as I know, its uplift, or from being oceanic rock and being uplifted, is relatively recent. I can't put a number on that specifically, but let's say the last 30 million years or so. But anyway, my point is that a lot of this material back here, a lot of these rocks are oceanic-based rocks. They're oceanic sedimentary rocks, a lot of carbonates, a lot of limestones, dolomites, things like that. And those rocks are relatively young. The impact that we're talking about here is not like the Barringer crater in Arizona, where it's just right there laying on the surface. It happened, a couple thousand years ago, and the evidence is still there, giant hole in the ground. It's much more like something like not the Sudbury, but the Chesapeake impact crater. So the Chesapeake, if you remember, it's under layers of oceanic rock material. So impact occurred, sedimentary rocks are deposited on top, and then later we were able to see that. So quite similarly, this is actually all covered up, or at least for the most part. The superficial evidence of this is lacking. So there's also ways to get at the subsurface then, as we've talked about in the past, remote sensing. We've looked at seismology in the past as a form of remote sensing for the interior of the Earth and the crust. You can also do with the crust of the Earth gravity surveys, or to find gravity anomalies. An anomaly is just something that's maybe uncharacteristic to the rest of the things around it. In a gravity survey, would be able to show, if you're flying a plane with a gravitometer or a meter that's picking up on these different gravity anomalies, the sensitive instruments can pick up on rocks that are more dense or less dense. And that would affect, if that rock is more dense, then the center of that mass has slightly more gravity association with it than an area that's less dense, like say unconsolidated sedimentary rocks or very consolidated basalts or high magnesium lava rocks, right? Those two things have a much different gravity signature, just to be extreme about that. And those types of things show up in what are called gravity surveys, which are used a lot of times for oil and gas observations or oil and gas research, for exploration, and then also for metal exploration or ore deposits. Now, to go to this gravity survey then, this is a gravity survey that is showing that small change in magnetic susceptibility, gravitational susceptibility of some of these materials out here in the Yucatan. And you can very clearly see that this does make a bullseye-shaped ring of the very outside of what became known as, of course, the crater. And then the central peak that we had talked about, when one of these rocks is large enough that the rheology underneath of that impact crater, the rock there, turns into or behaves like a fluid very quickly, and it rebounds back up and gives a central crater to this. So this is one of the ways that the Chicxulub impact crater was identified, was by a gravity survey like this. And then since it's been drilled both for oil and gas exploration, and then also just like the Chesapeake, are very similar to the Chesapeake exploration, but also for scientific surveys. So I think about 3 or 4 years ago, there was maybe a little bit longer than that, but results came out about 2 years ago. There were a number of scientific drilling programs involved in trying to drill into, I think, only three or four areas of the entire crater. And one of those was to drill into the central peak to try to understand a bit more of the dynamics of how this area reacted during the impact. I think that's really, really cool. A whole bunch of details I'm not going to go into, but just letting you know that they are there. The details are there. The picture isn't just as simple as rock hit the earth, asteroid hit the earth, and the dinosaurs are dead. Okay. Yes, that's a nice and familiar story, but there's layers and layers and layers to this story to be discovered, of course, through the rock record. Now, coming back around to this image, this is quite a bit different of an image, and this is, I wouldn't say completely not related to the Chicxulub impact crater and the rest of our material today, but this has to do with these words, mass extinction. The mass extinction, the end of the dinosaurs, right? Of course, we all know and love, we know of, let's say, this asteroid because of the demise of the dinosaurs. And this word, mass extinction, of course, extinction, you're probably familiar with that, like animals go extinct or have been driven to extinction. We've heard of this a lot, very probably, but this word mass, that means a mass amount, right? A massive quantity of these things. So we'll talk in a few weeks, a whole week, on all of the mass extinctions that have occurred on Earth, and we'll talk about the criteria for those. But one of the criteria is to consider something mass is it has to have the overwhelming mass of the stuff, right? So if you take all 100% of all organisms that were living during that time, and half of those things or over half of those things go extinct out of this whole 100, over half of those things go extinct and they're gone, I would say that that's the most massive amount of that 100%. And in fact, during the dinosaur killing impact, right, the demise of the dinosaurs, they weren't the only things around during the Mesozoic, so they weren't the only things that suffered the extinction. 85% of all species went extinct during this time. We'll come back to that in a few weeks. This graphic down here is about mass extinctions and also shows how geologic time is divided really, really well. This on the x-axis here is millions of years starting at 542. You know that date as the Precambrian, all this stuff back here, all the way to 4.6 billion years ago. That's the Precambrian. And then the Paleozoic goes to 250 million years ago, right? Okay. Then the Mesozoic from 250 to 65 million years ago. And then into the Cenozoic, this little sliver of today. Now, I hope by pointing that out, you were able to notice that where I'm drawing these defined segments of time that we have defined, humans have defined these, right? They're not color-coded or anything, are defined by these large peaks in the graph. Okay, so then your question is, well, what is the y-axis of this graph? I'm really sorry that I didn't include the label here, and I cut that off. The label is the percentage of invertebrate taxa, or the diversity of invertebrate taxa. So invertebrates are things like clams, or even arthropods, bugs, and then also snails, gastropods, things like this. Any shelly creatures that don't have a spine, right? A non-vertebrate creature. And in this case, this is marine taxa, or those things that live in the ocean. Because those have a really good record. So we can see in one layer of the geologic strata a whole lot of these invertebrate creatures, and if depositional conditions don't change all that much, then several rock layers up, the same conditions should preserve the same creatures, and oftentimes they do, if those creatures still exist. Okay? Now, in some cases, creatures are existing, same stuff, same stuff, same stuff, same stuff, same stuff. All of a sudden, these creatures are gone in the next layer above, and they're replaced by a totally different ecology of new creatures, and maybe only few creatures, or maybe there's a lag time until new creatures start to come up. But that level is something that we would say, that looks different below than it looks above. So let's draw a boundary there, and that might be a geologic time division. Or, again, we draw these distinctions, Paleozoic to Mesozoic, by the absence or presence of different fossils. Dinosaurs are present during this time, not present during this time, right? This then, I just wanted to put up this image to kind of prime on the idea of mass extinctions. We are going to talk a little bit about the demise of the dinosaurs during the Chicxulub impact crater. I mean, that's the most charismatic thing about this, in that sadistic violence, earth violence kind of way. But I just want this kind of thing to be in the back of your mind for now. And here, labeled 66 million years ago, is the Cretaceous Paleogene mass extinction. Okay, going from the very end of the Mesozoic into the Cenozoic time period. All right. There's a couple of YouTube videos that I've linked here. Again, I'm going to not go through the videos while I'm videoing. The quality, of course, is not very good, and you should be able to find these links on your own. They're out there free, of course, on YouTube, just like this video. But to say a few things about them, this first one, I think this is a really well done video. It's called How Asteroids Really Killed the Dinosaurs, and it goes through a lot more of the details on both how big this thing was, what happened to the atmosphere as it was coming in, the brightness of the object, what happened several hundred kilometers away, what would say animals be experiencing at that, and it's only 4.5 minutes, 4 minutes and 20 seconds long, so it's really not that long, but it gives a lot of really good details about an event like this. Now, if you go back to the earlier material here, I gave a few programs, online programs, asteroid impact calculators, right? And from those things, you can basically make the same kind of picture as this video is taking us through with this impact. right? I mean, the difference here is the calculator, you have these numbers and you're doing this in your mind. Where the difference is that those calculations and those numbers and the visualizations have been made into a really impeccably well done video here that we can take a look at. And the graphics are just very, very good. So take a look at that. It goes through a lot more of the details than I could probably give very well here. Then I like this video. It's a slightly lower quality video, but instead of showing all the details about the impact, about those moments surrounding the impact and how that had a devastating effect on life immediately, this one instead goes through kind of an event timeline and shows what the Earth globally and regionally in some of these areas would have been like for just a couple of days, a week, months, years after the impact. So this one really shows the lasting effects that this had on the global dynamics. And then from both of these combined, I think you get a really good idea of just precisely how this really caused the demise of dinosaurs, of ammonites, and many other lovely creatures that existed at the very end of the Cretaceous time period. Okay, so take a look at a couple of these videos. You can pause, of course, our main video and go take a look at those now. Would be ideal. All right, now to a little bit more of the evidence, right? That's I hope one of the details that you're getting out of this class is sometimes these stories are familiar to us. Like, say, the story of Snowball Earth. Now, it's not that out of left field that I wouldn't be surprised if a percentage of people who've taken this class, if you've heard of such a thing before, maybe in popular news media, or maybe some new news story hit and there's a science journalism piece on it, or maybe by scanning things like YouTube, or actually, I think that was an event that the new Cosmos series, Neil deGrasse Tyson series, covered in some amount. So some of these big stories, these big violent things, you've probably heard a little bit about. But I hope that the course sets apart from that to give you more of these supporting details, the scientific details, the research details that have helped uncover these stories, or that have helped give them a lot more elaborate details that really happened, rather than sort of filling these things in with fantasy or mythology, right? Because this isn't mythology, this is scientific knowledge. All right, so one of these great details here is, of course, if this impact, this bolide, it hits the Earth, and all of the ejecta that's spread out afterwards, as well as everything in the surrounding area that's burning, right? All of the forest fires that are occurring, all of this atmospheric material that's being spread circumboreally around the planet has to come out of the air sometime, right? Eventually, these particulates that were ejected up, whether this is soot or whether this is water molecules that were vaporized and put into the atmosphere, a lot of this stuff is heavy and eventually precipitates out of the atmosphere. Just like, say, today, even my breath, carbon dioxide going into the atmosphere is eventually absorbed as a particle into the ocean, first gaseously, but then forms limestones, as we've talked about before. So what goes into the atmosphere oftentimes does come back down into the geosphere somehow. That's one of the great connections between the two. And this impact crater, of course, is not any different. Well, it's different in a slight way, is that there was so much junk thrown up into the atmosphere that a lot of it came down and made a pretty discrete layer around in a lot of places that were depositing rocks at that time. So it's not like, say, Mount Everest, right? Mount Everest, if this happened today and Mount Everest was covered in asteroid ash tomorrow, Mount Everest is steep, mountains are steep, and the rain and the snow and the wind are eventually going to take all the material off of the mountain and put it somewhere else in a depositional basin. So not everywhere uniformly around the world is there a nice layer that's showing this asteroid impact. But in some of those unique depositional settings, they were accumulating sediment beforehand, and then this event occurs, there's sediment that continues to deposit afterwards. But the sediment that happened, or that deposited during that time, is very peculiar. Very peculiar. And here's actually a really good picture of this, and I thought this was interesting and relevant. A student back when I was in Wisconsin, Rachel Scott, I think she ultimately did turn out to be a geology major, and her dad, I believe, had purchased a piece of this layer of rock. Okay, so she actually had a gym quality sample of this layer of rock. Now, what's so special about this layer of rock? Well, first of all, it's pretty visibly different, right? You can see that, first of all, that the rocks down here, they're more shaly, they're more broken up, and same thing up here. You basically they look the same on either side, maybe a slight color contrast between them because of the organic material. But the layer between them is very discretely different. And in this case, it's harder, it is more well cemented together, and turns out is a lot more clay-rich than either the shaly material below this, which is a mixture of silts and clays above. But this is mostly and exclusively clay material. And now it's peculiar. But if we take a look at this layer discretely, which people have done, this is the pinnacle paper of this from Science in 1980, where Luis Alvarez and Walter Alvarez, and of course they're partners in all of this, right? Chemists and physicists. These two, who the same name, are a father and son duo team. I'm not sure if this is their first project together, but Luis Alvarez is not a geologist, but instead a chemist, and I believe Walter Alvarez's son really got him into this problem as a geologist, looking at this layer. Now, this is an area in France, I believe, in a fairly famous quarry, where this is very well exposed, and this is just one of the half a dozen locations around the world where the Cretaceous-Paleogene boundary is very well exposed, and you can find dinosaur bones below that layer, like say in North Dakota in the Hell Creek Formation, and then above that, no dinosaur bones. There's maybe the random thing like tooth or femurs that may be found above there. I don't know that for sure, but imagine everything goes extinct and it's dead, and then dead bones are floating around. I could see there could be the rare occurrence of some of the bones a little ways up in the geologic record, but a lot of them below, and then none of them above. Now, in this one, there was the question, well, why is this layer so much different? I wonder if there is a geochemical signature of how different this layer looks. Well, first of all, clays and silts would show a slightly different geochemical signature, so you could learn something from that. But also, geochemically, the chemistry of this stuff turned out to be very, very different. Not just a little bit different, like the difference between silts and clays, the crystallography there, but chemically, from the periodic table, incredibly different. And the difference is, it's really well shown here in this gigantic peak. This is the element iridium, IR, and in the Cretaceous, we have no detectable iridium. In the tertiary rocks, so here in the Cretaceous rocks, no detectable iridium. In the Cenozoic rocks, the tertiary rocks, no detectable iridium. But at this layer, at the Cretaceous-Paleogene boundary, 1,000-time increase in this element iridium. Okay, so what is iridium? What's so special about iridium? Iridium is a naturally occurring element on the periodic table, but is only known to occur at any measurable quantities, maybe I shouldn't say measurable quantities, any very large quantities in meteors that you could pick up, right, that came from space, cut open, they have those nice geometric patterns, iron and nickel crystals together, or chondrites. Any of these types of meteors that can be picked up and displayed, they have high amounts of this material, of iridium. So it became known and associated that iridium is not an element that's very common on the silica-based Earth, but instead is an element that is common or was common in the early formation of the solar system, which is the leftovers. It's the leftovers from that formation that are the asteroids and the comets that are out there in the rest of our heliosphere that are still going around the sun at different at different orbits than we are. So this iridium layer, this 1,000 times more iridium layer, that caused major questioning, and of course, then the interpretation, as we all see it up here, is extraterrestrial. Extra being outside, terrestrial being the Earth. So an extraterrestrial is just something that's from outside of your system. So a bolide, an asteroid, a comet, all those things are extraterrestrial, not just aliens, right? But that word describes anything from outside of the Earth system. So it was the iridium layer here in clay that raised the first question. I wonder if something from space could have been involved in the demise of the dinosaurs. Okay, of course, this is 1980. This is long ago. Now this is in all common children's textbooks. We all know of this story, but it's important to point out that we have very good discrete evidence for that. Well, what about the impact crater? Okay, the impact crater wasn't known for another 17 years, I think, after knowing about the iridium layer. So it was the rock that was the first example, but no impact crater was known for this, right? Until decades later, an impact of the same time and the magnitude, the size of it, was found. Okay, I think that's pretty cool. That's some good predictive scientific tools there. So in this video, again, you can pause the main video here, the lecture video, and go ahead and visit this conversation with Walter Alvarez, talking about that experience. And I think there's portions of this that are relatively moving because he's going back and talking about his interactions with his father and other colleagues, and then broader than that, how people didn't really believe them or wondered what was going on. But this 7.5-minute video really describes Walter Alvarez's, as a young scientist, as a young geologist, his experience investigating this and coming up with this hypothesis in this pinnacle paper. Okay, a very good short conversation with Walter Alvarez. Okay, so let's take a minute to talk about the dinosaurs. I'm not a paleontologist by trade. I've actually never really studied dinosaurs. I don't know a heck of a lot about dinosaurs. I was not one of those kids that was totally focused on dinosaurs and getting to know their names or any of this. I have had some good exposure to dinosaurs, both in my geologic studies, as you would imagine, but also in the area that I grew up. I grew up in western South Dakota, and while I was a young man living in Sturgis, South Dakota, and then moving out to a small town called Faith, South Dakota. That town was located about 40 miles south of where the most complete Tyrannosaurus rex ever found was being excavated. At the time that I moved out to this area, it had just undergone its excavation, and of course there was a lot of drama that unfolded about this. This is also known as the Dinosaur Sioux, or Dinosaur 13. There's a really good documentary movie about it. Anyway, my long-winded point here is that I was kind of exposed to dinosaurs being found in rocks and dinosaur fossils like T-Rex and Triceratops, or at least other ceratopsians, from my local area that I grew up in. So I had some awareness of dinosaurs, and still do to this day, but I've never been dinosaur obsessed in as far as paleontology goes. But the Jurassic, of course, is one of these, it's a very pinnacle word for dinosaurs, right? Remember, Jurassic is a time period. You have the Triassic, Jurassic, and Cretaceous. So the Cretaceous, being the very end of the Mesozoic, it's the Cretaceous dinosaurs that went extinct. The Jurassic dinosaurs, who actually were a whole different ecology, right? Both because of plate tectonics and global environmental climatic changes, as well as evolution. The Jurassic animals were not the animals that we see in the movie Jurassic Park. I just think that it would have been there's probably reasons for this, that Hollywood frowned a little bit more on something called Cretaceous Park than Jurassic Park. Maybe it doesn't sound as cool. But anyway, all of the typical dinosaurs that you think of, all the way from a Jurassic animal like Stegosaurus to a Cretaceous animal like Brachiosaurus, all of these things, the typical dinos, are those that lived during the Mesozoic, but particularly during the Jurassic and Cretaceous. The Triassic animals looked a little bit different. There was also a mass extinction between the Jurassic and the earlier Triassic, or coming out of the Triassic, that changed the morphology of these animals. We'll talk about that in a week or two as well. So all the typical dinosaur species that you're knowing and thinking of, it was those, of course, that are killed by that asteroid. Now, again, I'm not a huge dinosaur buff. I don't know all the details about all of these creatures. But one of my favorite things about dinosaurs is, of course, their relationship to modern day birds, or what we call the non-avian dinosaurs. That's literally what paleontologists refer to dinosaurs, the non-avian dinosaurs, because avian dinosaurs, or birds, still exist today. They didn't go extinct. That whole line of those things did not go extinct, but the non-avian dinosaurs, of course, did. A lot of this, for decades now, this has been discussed. Like, holy crap, dinosaurs had feathers? Back, I believe, in the late 1980s or maybe early 1990s, a very famous dinosaur was quarried out of a province in China. This became known as Archaeopteryx, or the ancient bird. And here's Archaeopteryx in all of its glory, in this shaly fossil, extremely well preserved because of the fine sediments and the clays here that allowed amazing preservation of this animal. In a lot of conditions, if say you have a lot of sand or a lot of higher energy influence into the environment, this type of preservation wouldn't occur. Usually what we see in fossils are the bones, the hard parts, the teeth, right? We don't see the guts and the muscles and the hair and the fibers and this kind of stuff very often. It has to be exceptional preservation. And that was the case in this area in China. It's this exceptionally good fossil quarry. And in that fossil quarry is Archaeopteryx. All the skeleton is here, but also very clearly showing this outline halo of feathers. Feathers, very long feathers coming off of the hands, very elongated fingers, very elongated one digit that is connected to these filamentous feather-like appendages. And then even out here on the tail, which of course modern birds have effectively shed their tail, or evolutionarily shed their tail, and just have feathers that serve as the tail. But at this time, being a dinosaur still has a tail that is also a feathered tail. So again, this is the animal Archaeopteryx. Here's a funny little reconstruction from the National Geographic. I can't remember what year this was, but National Geographic, about a decade ago, did a very good cover story on the non-avian dinosaurs and the transitions that we know of between early birds. This Archaeopteryx feather is 150 million years old. The Chicxulub impact crater is 66 million years old. So there's a good chunk of time for animals to go from early still dinosaurs that are feathered into birds before the impact crater. And as far as I know, there are suggestions that dinosaurs didn't it wasn't the ancestors of dinosaurs that lived through the mass extinction that became birds. Instead, birds had already begun to diversify before the mass extinction, and then some of those clades made it through. So birds did exist, as far as I know, in the very end of, or towards the end of the Cretaceous, and then it was those creatures that made it out. It wasn't the, anyway, I won't dwell on that too much more, but I just like this idea of thinking about dinosaurs that we know and love with feathers, like Velociraptor. Velociraptor is Velociraptor mongoliensis that we know very well. It's preserved with some of its fossil feathers. And then even a lot of people have argued that Tyrannosaurus rex here, one of the most well-known and loved of the carnivorous dinosaurs, right, of the meat-eating dinosaurs, is also like a giant chicken. It was probably feathered. Here in this artist's rendition, they're showing a very feathered tail, and then also these types of wing feathers that are coming off of its tiny little hands, tiny little arms. But kind of for some reason, feathers just look silly on these animals because partly they're naked, and then they also have these weird filamentous feathers. Maybe it's just the reconstruction, but it kind of takes some of the terror out of the Tyrannosaurus rex, right? Maybe, kind of, I don't know. But here's a good phylogeny, reconstructed phylogeny from the fossil record of the transition between dinosaurs to birds. So there's two major classes of dinosaurs. I'm not sure if I'm using the word class correctly. They might be orders of dinosaurs. The sauropods and the theropods, or the lizard-hipped and the bird-hipped. And those two words arise from today's modern lizards and birds. If you look at their hips, they're very clearly different, but they both share qualities of reptiles. Clearly, a lizard is still a reptile, but birds, it's been known for a long time, have a reptile-like skeleton and hips specifically. So dinosaurs started to be named based on their styles of hips, and fundamentally, the easiest way to think about this is two-leggers. Two-leggers are more like bird hips, like today's birds, and then the four-legged dinosaurs were of the sauropods are the lizard-hipped type. Well, the lizard-hip types, boom, they're gone. Never to return again, not birds. But the two-leggers, or the theropods, those do have the phylogenetic tree that's organized to include modern day, or at least closer in this diagram, to modern day birds. You can see that there are several splits after these from things that eventually did go extinct, that are still much more along the lines of dinosaur-like things. But as you can, I hope you can fairly clearly see here the evolution of the wing and the evolution of the lack of the tail and the tail feathers, and then slowly ramping up to a more flight-bearing bird, or more typical bird than we would think of an animal like this, which is probably something like gliding along the ground. There's a short video here from the Natural History Museum that does show this transition. It's a computer-generated video, so the link is up here. This is only about three and a half minutes long, but it's called Transition from Dinosaurs to Birds. And the computer graphics are a little bit hokey. I mean, just to give you fair enough warning that it's not a I mean, it's still really good animation, and it really brings this to life. But there are some of the things they do with the animals, and the linear thing. It really does make it look like they were linearly transitioning from this thing to this thing. Like all of a sudden, I just sprout wings and take off. Some of the things that they do here, and I don't think they're not portraying this as accurate. They're just giving a good succinct view at how we know in the fossil record the steps of these things actually looked. Okay, but it's a very good video. It gives us a really good perception on that transition between dinosaurs to modern day birds. I think it's pretty darn cool. Now, on to something a little bit more exciting. All right, I said a minute ago that feathers make Tyrannosaurus rex just look just look like a friendly, average character then, right? You're not so scary, okay? But if you take a chicken and you blow that up to the size of the Tyrannosaurus Rex, I'm now again very afraid of this, okay? Like, look at this massive Chickenosaurus, right? We'll come back to that statement in a minute, but the idea now of birds being large or carnivorous is very scary. I don't know if you have, if you've ever seen a flock of chickens together, or but they're vicious to each other, right? And they're pecky little animals, and all this. So chickens as dinosaurs, very scary to me. Well, in fact, because of this relationship between modern day birds and their ancestral DNA being common with the clades of dinosaurs that went extinct, I'm not going all Jurassic Park on you here, okay? But these were some of the ideas then for Jurassic Park. Now, today, instead of the idea that was proposed in Jurassic Park, that if you have this DNA and then you fill it in with modern animals, then maybe we can make a complete DNA. That's certainly not in the realm of genetic availability of what we could actually do. But if you have the genetic code of a material that already exists, and that can be manipulated for certain genes to turn on or to turn off, or say to not release the enzymes for that gene to be debilitated or to not do something, then that manipulation is enough to change the animal overall. So this all comes from a TED Talk by Jack Horner, who is a paleontologist from the Museum of the Rockies. I think at one time he was the lead paleontologist there. Basically dinosaur guru type of guy. He was the paleontology informant for Jurassic Park, for some of the accuracy of the dinosaurs and things like that. You can hear all about that in his talk, Building a Dinosaur from a Chicken. Yeah, that's the name of the talk, Building a Dinosaur from a Chicken. The link can be found over here. And in this, he's pointing out that we know of genes like the gene that tells the chicken embryo to stop growing a tail. And if that gene can be disassembled or can be told to not do that, right, genetic manipulation, then we can maybe grow a chicken embryo with a tail. And that's what's circled right here. Or we can force a chicken embryo, instead of all of its fingers that it has at the beginning, to be fused together. Instead, if those can be, that gene cannot do that, then we could probably grow a chicken with 3 fingers, which is what dinosaurs have, I think. Then in another one of my favorite examples, this comes, I don't believe this is addressed in the TED Talk, this comes from another paper, the development of Archosaurian first-generation teeth in a chicken mutant. That sounds terrible. Anytime you have mutant as part of the word, or chicken mutant, that just sounds terrifying. But yeah, this team of anatomy scientists, part of them out of University of Wisconsin-Madison, were able to manipulate the chicken genes to force this embryo to grow teeth. Yes, chicken with teeth, chicken with claws, chicken with tail, chicken very scary to me now. Okay. But that's the idea behind this, is that if today we have the modern day chicken, maybe it is possible to genetically manipulate that to turn it into more of a thing kind of like a dinosaur. Rather than going back to dinosaurs, maybe we can force the chicken to go forward into a nice, house pet sized dinosaur. Sounds terrifying. Okay, all right, that's just some fun for us. Okay, let's go back to the impact crater. Now, again, we're familiar with the story. Rock comes in, obliterates stuff, causes a nuclear winter, kills the dinosaurs. Here's another really cool detail, I think, that's left out of this story. Mostly because this wasn't really well investigated until even the last 5 years. Most of this material comes out of a paper in 2015, only a couple years old. but people have been hot on the trail of this idea for a little while. Now, we're going over to the other side of the globe, right? So here's your globe. Asteroid comes in, it hits Chicxulub or the Yucatan Peninsula on one side of the Earth. On the completely opposite side of the Earth, not direct opposite, but pretty close, the opposite side of the Earth is the subcontinent India. On the subcontinent India, which is in a slightly configuration 66 million years ago, but we're just looking at today's extent of these rocks. This is meant to represent a geologic map and the distribution of these rocks in red called the Deccan Traps. The Deccan Traps are basalt lava fields that are widely extensive across this entire western province of the subcontinent India. Now, these are 66 million years old, so they're not like lava rocks like Craters of the Moon National Park or some of these lavas that you can go out and walk on today. These are more akin to, in my own local area, if you have driven the Interstate 84 between, let's say, Pendleton, Oregon, and down the Columbia River Gorge to the Dalles, or then to Portland, and you're driving down the gorge, all the rocks on either side of the Columbia River Gorge are lava flows, individual lava flows that you can see, these tabular layers, and then between them some soils that have formed or that had formed, and then new lava layers, new lavas, and so on and so forth. Those are what are known as the Columbia River Gorge basalts. Basalts are lava rocks. So the Deccan Traps are kind of like the Indian equivalent of the Columbia River flood basalts, or Columbia River basalts, times like 3 or 4. There are higher, or there's a larger stack of them, and they also extended over a much wider region. So overall, their volume is literally 3 to 4 times, I'm not sure the exact number, larger than those that are in my backyard. Okay, point is, 66-ish, well, between 63 or 61 and 70 million years ago, this portion of Western India was just pumping out volcanic lava flows every couple thousands of years, every 10,000 years. New lava flow that blankets the entire area. Okay, soil forms, 10,000, 5,000 years, new lava flow. Okay, these are what are known as large igneous provinces, or LIPs. These areas that experience over the period of 1, 4 to 8 million years high amounts of volcanism. Again, they're also termed flood basalts in that case. All right, so the Deccan Traps here, this is also a pretty good picture showing these stacks and stacks of these things like pancakes stacked on top of one another. Okay, and then the map showing the distribution. Well, what does this have to do with the Chicxulub impact crater? So first of all, the timing. Hopefully, saying 61 to 70 million years ago, you're kind of like, okay, that's about the same time as the impact crater. But this is over 9 million years, where the impact occurred all at once, right? Absolutely. So nobody is saying that this lava was made by anything to do with the Chicxulub impact crater. Except, if you look closely at the materials themselves, this is kind of a little creation diagram of how these form by mantle plumes, kind of like the Yellowstone, the plume that's beneath Yellowstone forming the supervolcano there, similar situation. But to go back, if you look at the distribution and the volumes of these materials, and that is what is talked about in this paper from 2015. Here is marked 61 to 70 million years ago, 66 million years ago. And even by just this line in this diagram, you can see each one of these bars is representing one of these major lava flows. That counting up along this bar, you're going to count a lot more along that line than you would along that line or would along that line. So making the argument that this time period, about 66 million years ago, as far as the Deccan Traps go, were the most voluminous time period any time in that 61 to 70 million year ago interval. Any time in this 9-year interval, the most volcanic time was during or after the Chicxulub impact crater. I think that's really neat. These are volume estimates that are over here that support this as well. The YE group, I think that's how you say this. This is what the researchers are arguing. They saw a major increase, and by their volume calculations, this group did experience, here's the normal volumes, did experience a major volume increase just after the Chicxulub impact crater. And the paper here is called Triggering of the Largest Deccan Eruptions by the Chicxulub Impact. And you can find that on the Canvas website for the class. This is one of the reading materials that I have put up for this week for perusal of some of these details that you can look at. Okay, so let's step back for a second here. What is this science gobbledygook telling us about the story then? So story is rock is hurling from outer space, carrying iridium, right, from outer space, and it goes into the atmosphere, begins to volatilize, and slams into the crust of the Earth, which volatilizes the waters, volatilizing the atmosphere, making plasma, and kicking up all this fiery dust that's making forest fires, and the shock wave that is sent, earthquakes that are sent around the Earth, reverberating Rayleigh waves, reverberating around the crust of the Earth. On about the opposite side of the Earth, they're causing all these interference patterns. Probably, this is what waves do. They cause interference patterns on the other side, which happens to be an area that is already experiencing massive amounts of volcanism. So under that disturbance, the volcanism increased for a period of time to pour out a lot more of these basalts on the opposite side. So as a direct result of this impact crater is another insult to that previous injury, right? I'm sure you've heard a saying like that, adding insult to injury. And I think that's a really interesting part of this story, is that it wasn't just the asteroid, that there were more things involved. So volcanism, okay, well, that's just happening in the surrounding area then, right? That's just, isn't that just the poor animals that are over here on the Indian subcontinent that are experiencing that? Well, volcanic gases that are emitted to the atmosphere are also known to change the overall climate. Go back to a little bit of volcanism from that discussion and recall that after Krakatoa or after Toba in Indonesia, that both of those events, because of the sulfur dioxide in the atmosphere, were triggers of global famine during those next couple of seasons because of the gases that were put in the atmosphere. So an event like this is already changing the face of the Earth with the output of gases, but then impact, major injury to the globe, and then a little bit more punctuated, or a little more punctuation in the amount of volcanism. Okay, also a completely separate paper now to add a little bit more insult to that previous injury. The Deccan traps, by this time, they're pumping out volcanism, but it turns out that some of that volcanism towards that time period, this little peak that's right here, okay, from, let's see, the times, this is 66 million years ago, so let's say, by 65 million years ago, something that's occurring here is an increase in the amount of 65 million years ago to well beyond the impact, is that mercury, the actual content of the gases here, also contains vaporized mercury that's being put out into the atmosphere as one of those gases. Okay, mercury is, of course, extremely poisonous to any animal body, right? This is a material the body cannot handle very well, something that causes the neurons to misfire and to degrade, and overall, in humans, to drive us mad, like the Mad Hatter, right? So mercury, bad. Mercury in animal environment, bad. Mercury in ocean, bad. Causing bad things. But it turns out that for a slight period of time before the impact, Mercury was on the rise because of these Deccan traps. And it may have been being sequestered in the ocean or in other biomes around the Earth that was already starting to cause maybe a decrease in biodiversity or a decrease in, say, the livelihood of infants or disfigurements or any number of things were occurring to organisms by the output of this mercury before. And then during the impact, more volcanism, more mercury, again, more insult to that injury. So I think this is a really brilliant, perfect storm that's happening here, right? And we know so much about this because it is a very charismatic time period. We want to know a lot more. And I think in some ways, this whole elaborate story of it being the impact and the volcanism and the mercury, in some ways is a relic of how infatuated we are with this event of violence, right? The more we investigate it, of course, the more we're going to know about it. And that's just Earth history in general. The more we look at any one time period of rocks or any package of rocks, the more complete and more elaborate and more details come out about that story. And that's Earth history in a nutshell. But I think this is really really neat to understand that there was a lot going on during that impact. Okay, well what happened afterwards? Of course, the dinosaurs are gone, right? So what happened to life afterwards? 85% of all species go extinct. So what the heck is left? Basically anything that could not be in the atmosphere for too long, right? The atmosphere is toxic. This is like a nuclear winter. The sun is blackened out by the sky, so photosynthetic organisms are having a tough time. Really scavengers. Think of anything that can basically scavenge on whatever is available, like omnivores, not carnivores, and not herbivores, things that exclusively eat plants or meat, but things that can kind of eat about anything, right? That are scavengers, that can kind of eat a whole variety of stuff. Those are things that were more likely, say, to make it through the mass extinction and then to come out and start to repopulate on the other side. Okay, so what was going on afterwards? Well, if we look at the fossil record for this, one of my favorite organisms of all time, fungi, seems to have had a peak, a major peak in the amount of fungi that existed during that time. So here's again the late Cretaceous. Here's the Cretaceous tertiary boundary, or the Cretaceous Paleogene boundary, and then the Paleogene, or the Paleocene. Right at the Cretaceous boundary, here is the iridium layer, the huge peak in iridium. But also, if we look at the spores that are contained within those layers, so spores are a material that ferns or conifers or fungi, very lower, not seed-bearing plants, not flowering plants, they put up into the atmosphere, and those spores can drift along on the atmosphere and then eventually deposit somewhere. So we can see these spores in clays, right, or in areas of rocks that have deposited on the surface of the earth. And if you look at all these different species, ferns and podocarps and angiosperm taxa, flowering plants are gone, right? Ferns, fungi. Okay, everything else has a break right here after the Cretaceous into the Paleocene. Everything, all of these things seem to have a break except for the fungal spores. Fungi seem to be the only spore-bearing material. It's not the only thing that's made it. There inevitably has to be some of these things that made it through to repopulate on the other side if they're present. But the overwhelming amount of organisms that were taking advantage of this time where the scavengers rule the earth were the fungi, right? So this was a time where fungi probably ruled the earth, right? They inherited the earth from this destructive time period. And fungi do a lot of things in the ecosystem very well. They're the pioneers of any soil, of any area that is disturbed. They're the first pioneers. They're the ones who kind of set the soil and the organic material. They're the one who sets a lot of the stuff in motion. They're the first primitive things to come in to start cleaning things up and to preparing the area, the soils, for later organisms. And they certainly seem to have done that when they inherited the earth, is they were able then to kind of get the biomes back in order and get ready for organisms to repopulate. I think that's a really fascinating way to think about that. A lot of this idea and how I explain that comes from a TED Talk that's also linked in the Canvas in the extra credit materials. Paul Stamets, major fungal guy, major mycophile, or person who likes mushrooms or likes fungi. And I think the talk is called 6 Ways That Mushrooms Can Save the World. And this image is very early in his talk, and he talks about this very same thing. When the asteroid impacted the Earth, everything else died. Well, most things, a lot of things. And the scavengers, the fungi, took over the Earth. Okay, now, so that's probably what was going on afterward, is that fungi were able to set the stage for life to repopulate, and then we are at today. We'll pick up on a little bit of that evolutionary discussion later in the term, but for now, we'll leave life alone for a little while. Now, I want to transition a little bit out of the Chicxulub impact crater, okay, and back into asteroids just in general. Okay, so we started this long conversation with asteroid impacts that we can see on Earth today. So we know that they occur. We know that they've occurred billions of years ago in the case of, say, the Beaverhead impact crater. And that they also do cause mass extinctions when the rock is large enough. All right, so that does bring a level of concern to us, right? If we know that one of these rocks hurling from outer space can obliterate life on Earth, well, not completely obliterate, but can, let's say, decimate life on Earth, then that could be a game changer for the human species, right? Now, because we're so good at space-age technology, I mean, really, we're way better at it than deer. I mean, how many satellites did deer have in near Earth orbit, right? None. So, us being the species that's kind of responsible for the space-age stuff, and we also know about this thing, it's also really neat that we can go out there, we can look, right? We are the eyes of the world, as has been discussed, and we can go look for these random rocks. Well, they're not so random. It turns out they are on an orbit around the sun, just like everything else. And their orbit is perturbed by all the other planets that they pass, right? They get too close to Jupiter. Jupiter totally changes their trajectory. And same thing with Earth and all the other things. So they have an orbit. They come back around all the time. And turns out because we kind of have a phobia of these things now. I mean, come on, they can obliterate cities or regions or, the Earth, all life, mass extinctions. We kind of want to know about those that are big enough to do that to us. This is a table. This was taken directly off of Wikipedia about a year ago, 2 years ago. But these statistics are from NASA, and this was made by Alan Chamberlain at JPL. But this shows essentially the diameter of these objects and the quantity of those that are known. So of objects that are between 0 and 30 meters, 30 meters is pretty big. 0 meters not so big, right? But 1 meter, I mean, that's this size. We don't know of very many of that size of rocks. Those are really hard to find. But things that are, say, the size of half of this building, that's a lot easier for us to find, which is more close to 30 meters. So things that are between 0 and 30 meters, we have found almost 3,000 of those that are monitored. Their trajectory is calculated, where they're going to be going close to some other, say Saturn, and if they're going to change their trajectory, people are looking at these sorts of things. 30 to 100, 100 to 300 meters, and 300 meters to a full kilometer in size and diameter, or those that are above a kilometer. We know of 1,000 things that are out there that are larger than a kilometer in size. And those are the really scary things, right? These are the big things, the size of of entire towns that are out there. It's a big rock. Okay. So point here is near-Earth asteroids. We do know of them. We aren't completely blind like the dinosaurs were. We are the eyes of the world. We can see that some of these things are out there. And in some way, being able to see and to know that the things are out there makes them a little bit less scary. I mean, we know they're out there, and if we just leave it at that, and it's totally mysterious and they can hit us tomorrow, that's kind of scary. But to actively be looking for them and to know what's going on, that gives us, at least me, a little bit more confidence. Now, the next question is, what the heck do we do about it, right? And that's a much harder question to answer. But at first, we can't address the what to do about it unless we first know about it. There's also really, the nuclear warhead idea in Armageddon is not the top idea. Okay, that is not what most people are thinking should probably happen with an asteroid if it is hurling towards us. This is one of my favorite ideas. There are several that are out there, but if we know about this for say multiple moon distances away, and we can go out there and meet the object, and remember that the way that gravity works, mass 1 times mass 2, and their relative distance apart. If this object is way far away from Earth and the moon, it's not within our gravity well yet, if we can kind of put large objects around that and kind of pull it off of its pull it off of its orbit using gravity, then we can kind of give an asteroid a soft nudge off of the trajectory where it would hit Earth. So that's a pretty good idea. It's a non-violent idea. It doesn't require bombs. It also basically prevents a near-death experience of the entire globe. So if you're interested, there are others that are out there. I think I can probably find a TED Talk about that and link that in the show notes as well. So we do know of them, and we also know how scary they are. We also have a scale on scariness, right? Just like your green code, red code, orange code type of stuff. Well, here's the code for how scary meteors or asteroids are. This is the Torino scale, and down here is the probability of impact. Here's 100% down here, and then the size of the object and the kinetic energy that would release. This is in megatons, which is the TNT equivalent, right, of the explosion that would be caused. Now, I just want to read a few of these levels that are here. So, for instance, something like the green layer, a routine discovery which a pass near the Earth is predicted and poses no unusual level of danger. That's a green. Okay, cool. Those things happen a lot. Now let's look at the difference between a green level and, say, 11 Seville threatening. A very close encounter by a large object, which, if occurring this century, poses an unprecedented but still uncertain threat of global catastrophe. Okay, uncertain threat. So what we're saying here, by these levels, is we're also inherently putting in there the level of confidence that we have that this won't hit us. So these things are large and could cause global catastrophe, and but we yet to know if they're on trajectory to hit us or not. Then what about a level 9? A collision is certain, capable of causing unprecedented regional devastation, so on and so forth. All we need there is certain. So red is when we get to the level that we know that it's going to hit us. Either it's not that big, So it might just destroy, half of a country. Or this is really big, and this is going to cause a runaway global effect. Okay? And these things, here's one of the scary parts. Such events occur on average once per 100,000 years or less often. 100,000 years. That's what we're predicting, that these large global catastrophe type of things occur. Not Chicxulub size. I mean, that was major global catastrophe. But more so like something that is now being uncovered in Greenland. Yeah, underneath Greenland, as the ice is shrinking back, geologists have been able to, in looking at the thickness of the ice and is looking at some of the topography around this, but also the geology around this, and some of the sands that are coming out of the fjords that are draining this contain impact glass, right? They contain some of those the impact quartz, and it's now known that there is a sizable impact crater beneath Greenland. Was I saying Iceland a minute ago? Excuse me. Beneath Greenland, beneath the ice sheet in Greenland, that is quite possibly only on the order of tens of thousands up to 1 million years old. So we're still discovering some of these interesting impact craters. All right, so today's dose of violence is brought to you by the Alvarez team. Of course, here's the entire team of folks that were involved, the scientists that were involved in that Pinnacle 1980 paper. And then here's the father and son duo themselves, Walter and Luis Alvarez. And then here they are at the Cretaceous tertiary rocks at the boundary right here that they were able to look at those clays in the iridium layer. Okay, really fascinating story. I have one cleanup bit, and this is an image. I'm sure you can't see it very well on the video here, but this is an image of the Columbia-Nuna supercontinent. So it did escape my mind that I had dug up a paper a couple years ago on a good configuration of the Columbia-Nuna supercontinent 1.6 billion years ago. And in the lecture on quiescent crust and supercontinents, I did not give that reconstructed picture. In fact, I just kind of sloughed it off and said that it has no comprehensive configuration because it's so old. Where in fact, because, just like I said a few minutes ago, the more that we investigate these particular rock packages or periods of time, the more and more we learn. I mean, we can look at every single sand grain and probably write a paper on each one of them by what we learn from these things. So the more that we investigate, the more we know and understand. So quite a few years ago, there was not a very good reconstruction for this. But over the last decade, we have been gathering more of this detailed evidence about how the continents were stitched together at this time and what that likely looked like, where the subduction zones were, and so on and so forth. Then now we have a really good, decent reconstruction of that supercontinent. Pretty cool. Okay, and that concludes Violent Earth for today. And I'll make sure that this finally gets up on YouTube, and we'll talk to you in just a little bit for next week of Violent Earth, poison gases. Poison gases. All right.